Hi everybody! In this video, we're going to go a little bit deeper into acids and bases and what exactly they are. So, just by looking at the title, we're going to be looking at the different models for acids and bases, or in other words, acids and bases can mean more than one thing. Wow, right? So, to tell you the truth, in the Arrhenius model, which is the first model that we'll look at, the simplest model actually, acids form H plus and bases form OH minus in water. And an extra requirement for the base definition for the Arrhenius model is that the base has to have an OH in its formula to be considered an Arrhenius base. So you might be wondering what this thing is. Now, this is the hydronium ion. And to tell you the truth, the hydronium ion is a more legit version of the H+. So let's read the definition and see what exactly it means. So H+, upon contacting water, so water is H2O, becomes H3O+, so H3O+ is a hydrated form of H+. So anytime you see H+, it actually means H3O+, because since H+ is in water, it will automatically be hydrated by the water around it to form hydronium, H3O+. And this is actually, as you'll later see, an acid-base reaction. But we'll talk about that a little bit sooner. But for now, just know the Arrhenius model for acids and bases. So, according to the model, an acid like HCl would qualify as an acid according to this model if it forms H3O plus upon entering solution. So in this case, we can see that HCl and H2O can actually react to form H3O plus. Now you might be used to seeing that HCl becomes H plus plus OH. Well, no. H plus plus Cl minus, right? That's our traditional model. But this model is a bit more complicated, and it reflects the realities of the world that we live in. So how this one works is that the H plus will be transferred to the H2O, an acid-base reaction or a neutralization reaction. Either one works. And you end up getting Cl minus plus H3O plus. So it satisfies the requirement to be an Arrhenius acid because it forms H3O plus in solution. Now, as I just mentioned, you can also write it in its simplified form by saying that HCl aqueous ionizes into H plus and Cl minus. It's easier, but not realistic. It's considered lazy, but it's still good. So I usually tend to stick with this definition, unless I deal with more complicated things. But I like this simpler version, to be honest. Now let's take a look at the Arrhenius base. So it has to form an OH, and it has to have an OH minus in it. So NaOH, sodium hydroxide, has OH in it, and it forms OH when dissolved, because it's a salt. So there you go. That's an Arrhenius base. Now NH3, it's not an Arrhenius base, even though we know it's a weak base, because it doesn't have an OH in it, but it does produce an OH, and as we'll see later, other definitions of acids and bases will compensate for this simple model and kind of expand the definition of what exactly acids and bases are. So the next definition that we'll look at might make things a lot clearer. Bronsted-Lowry, I don't even know if I pronounced that right. Acids are proton donors according to the definition, and bases are proton acceptors. So the idea about how the H plus is transferred, that idea holds true in an acid-base reaction, because in this case, this is the acid, this is the base, and we said that H2O can be either an acid or a base in our last video, so hopefully that makes sense. And in this case, acids are proton donors. HCl is a proton donor that donates its H plus to our base here, who accepts the proton, the H plus, and it forms H3O plus. Voila. And if you remember, H plus is also called a proton. We discussed that in our previous video, so check that out if you don't understand why these two are synonymous. So what about a base? Well, this is a Bronsted-Lowry base because it accepts NH plus from water. So this water is donating NH plus to form NH4 plus OH minus. So in this case, H2O would be a Bronsted-Lowry acid because it donates NH plus and thus accepts NH plus. So just by looking at that, we can deduce that this, by definition, is a base because it accepts NH plus according to this reaction to form the OH minus, of course. So from that, we can determine something very important that we have to know. In water, acids will produce hydronium. So you notice that HCl is an acid because in H2O, it reacts with the H2O that's in to produce hydronium via an acid-base or neutralization reaction where an H plus is transferred. Now, bases will produce OH minus in water. So this is a base, and in water, it reacts with water to form OH minus via transferring the H plus from H2O to NH3. So this definition of acids and bases, the Bronsted-Lowry model, will be the definition that we will focus on because it's the most relevant to what we will be discussing in future videos. But there's more. We won't see the last model a lot, but it's still important to know because it kind of is the core foundation for why all of this works. And it's the Lewis model of acids and bases. According to this model, acids will accept electron pairs. So an electron pair is like a lone pair, and bases will donate a lone pair. So to memorize this easily, you can think of it this way. Acids will donate H plus, but they accept electrons. Now the opposite goes for bases. Bases accept H pluses and donate electron pairs in any neutralization reaction. So yeah, so that kind of relates back to Bronsted-Lowry, where we said acids are proton donors and bases are proton acceptors. Now let's see how that relates to this definition. Let's take a look at HCl being a Lewis acid. So we know this is an acid, but how does this electron stuff work? Well, to have it work, we kind of have to draw all the Lewis structures for HCl water, which is the thing that's going to react with to form the hydronium ion. So this has a plus charge. I should have drew that. And so I drew all of these structures. So let me just write the reaction down here. HCl plus H2O becomes Cl minus plus H3O plus. Just like that reaction we just did up here. But we're going to draw it out, and let's demonstrate how this electron stuff works. So notice that this lone pair can kind of share its electrons with that H plus. So when you share electrons, you form a bond. And if you share a pair of electrons, you form a single bond. So this arrow that I draw to the H plus basically tells us that this O wants to share these two electrons with H, so it's going to kind of form a bond, which consists of two electrons that are shared. But if you think about it, H can only have one bond because one bond has two electrons, which is all H needs to have a full shell, since H only needs to fill its 1s2 shell in order to be stable, because that's its outermost shell. Now, if you have two bonds, which would happen if we connect the H and the O, and the H and the Cl, well, that's too many electrons. So that bond over there is going to have to stop sharing electrons, and the Cl is going to have to hog those electrons. So that bond will break, and both electrons will go to the Cl, and what you end up with is that the Cl, of course, has the extra 2 electrons because this bond basically breaks, and the 2 electrons are part of the bond goes to the Cl. Meanwhile, the H over here got connected to the H2O over here to form the H3O plus we see over here. So, kind of complicated, and you're wondering, how do the charges work? Well, that plus charge right there, you can easily determine by looking at the formal charge of oxygen. The formal charge of oxygen right here is going to be plus 1, simply because we know that oxygen naturally has 6 electrons minus 3 bonds minus 2 electrons that are non-bonding, which makes a plus 1 formal charge. And these 3 H's have no formal charges. So plus 1 plus 0 plus 0 plus 0 is a plus 1 for this ion over here. And remember, the sum of the formal charges is equal to the charge of the ion. So this makes sense. Now the Cl- has 8 electrons, one more than what it's supposed to have. So it's going to have a minus 1 charge. So that's how things like this work. And it is confusing, but it's similar to how we did resonance structures, where we moved electrons around to make sure that all the atoms are happy where they are at. And then in this case, we wanted the H to be happy, and in order for it to be happy, by bonding with that O, it kind of has to lose this bond over here to, make sure that it has 2 electrons at most, since that's what it takes to have a full shell, making it stable and happy. Now, let's take a look at how bases work. Remember, bases will donate electron pairs. So in this case, the acid accepted the electron pair, as you can see. The acid, or HCl, accepted that electron pair from that H2O. Now in this case, the base will donate the electron pair. So this is the electron pair, and it's going to donate it. And it's going to donate it to none other than water. Now this reaction is the same as this reaction over here, just all drawn out with the Lewis structures. And it's super important to draw it out in terms of Lewis structures because we want to see how the electrons travel. So since it's a base, this lone pair will try to attach itself with the H. But this H says, well, now I have 2 bonds, and that's one too many bonds because H only has 1 bond, or only needs 1 bond to be stable, since it only needs 2 electrons. So what H will do is it will decide to break this bond, and this bond has 2 electrons. It'll all go to the O. And what you end up with is this, where you have the NH4 plus, since it grabbed an H. So in order to keep track of the charges, whenever it grabs an H, it's like grabbing an H plus. So you become plus 1, more positive, and the one that kind of accepts the electron pair will be more negative. So in this case, this over here will accept that electron pair located in the bond, and that will make it more negative. So do whatever works for you to know how the charges work, or you could simply not look at this and rely on this, where an H plus is transferred, in order to figure out where the charges go. But either way, it's the same, and in the end, you have ammonium and hydroxide. So 2 different ways of doing the reaction, but this one is more visual, and it actually describes what actually happens in an acid-base reaction. So this is a Lewis base. And guess what this is? This is a Lewis acid because it accepted the electron pair. See, the H2O accepted this electron pair. So look at that. We're learning a lot. And so let's now talk about identifying acids, bases, conjugate acids, and conjugate bases given a neutralization reaction. And we will talk about what a conjugate acid and a conjugate base is. But the best way to talk about that is by doing an example. So in this reaction, I want to identify the 4 components. Since this is a neutralization reaction, it will have all 4 of these components that I just pointed out. So we know that HCl is going to be our strong acid, or we could just say acid for simplicity. Let's not introduce the strong and the weak because that's irrelevant. And we know that OH minus, for example, NaOH, we know that that's always going to be a base. And we kind of also know that it's going to, be like this is because we know that this HCl will donate its H+. So because it donates the H+, it is an acid. And because OH minus accepts this H+, it is the base. Now, when the HCl donates the H+, it will become a Cl-. So its conjugate, or what results from, after it gives up an H+, that result will be a conjugate base. Now, to tell you the truth, the rule for identifying conjugates is that the conjugate is always the opposite of what it was before. So in this case, before we had an acid, its conjugate, or what happened after it gave up an H+, will be the opposite of what it was. So in this case, since it's an acid, it gave up an NH+, then its conjugate will be a base, the opposite of an acid. Now, OH minus accepts NH+, and after accepting NH+, its conjugate will be H2O. But because OH minus was a base, its conjugate is a complete opposite, so it's an acid. And to be more specific, it's a conjugate acid, and this is a conjugate base. Now, if you notice, the conjugates are always on the right-hand side, so these are on the right-hand side, and the acids and bases are on the left-hand side. So hopefully that is clear. Now, let's talk a little bit about how to determine whether it's going to be strong or weak. So, if you start off with something that's strong, the conjugate of it will be very weak. So, we have a strong acid. The conjugate of that, we know it's going to be a conjugate base. It's the opposite of what it was. So this is an acid, this is a base. And this results after losing an H+, of course. And since this was strong, the conjugate will be weak. So you can say that this is a weak base. And in this case, since this was a strong acid, this will actually be a super duper weak conjugate base. Now let's look at the converse, where we start with a very weak base. So this is very weak base. It's actually not even considered a base at some points because it honestly just doesn't accept any H pluses naturally, because this reaction is so unfavorable that it will never happen. But in the case that does happen, the very weak base will, once you add an H plus to it, will form a conjugate acid. But since the base that we started off was very weak, the conjugate is very strong. So notice the trend. Strong original, the conjugate is super weak. Weak original, or in this case it has to be very weak, it will be a strong conjugate. Now what if you have let's just say a weak? So you might be confused about what weak and very weak is, but these are the three types of hierarchies I want you to know. There's strong, there's weak, there's very weak. And very weak, it essentially means that it's very, very weak, which means that it's not even like a base. So for example, Cl minus is very weak, which means that it's technically a base, it can be, but it's super duper weak that it doesn't behave like one. So in this case, a very strong acid like HCl will form a very weak conjugate base. And the same idea goes for a strong base. A very strong base will form a very weak conjugate acid. Now what happens if you're just a weak acid? Well, if you're a weak acid, you're going to form a weak conjugate. So like if you're in the middle, you'll form something in the middle. But if you're in the upper extreme, you'll, form the lower extreme, which is strong to weak. And if you're just right in the middle, well, your conjugate will also be right in the middle. So it sounds pretty confusing, but it's not very important, and if I were going to discuss this, it would be in a future video, not this one, because this is merely an introduction. So let's take a look at this example, and what I want is for us to determine the acid, base, conjugate base. So we know this is the acid and this is the base, and the conjugate of HF is F after losing an H+, so that's the conjugate base. It's a complete opposite, and that just leaves conjugate acid because OH is a base, and what results from it is, well, the conjugate acid. So let's, for this one problem, do the strengths. So this is a weak acid, and its conjugate will be a weak base. This is a strong base. It will form a very weak acid. So I kind of showed that hierarchy here just for some review, but it's not that important, so I won't go over it too deeply. I'm more concerned about this concept because this is the more important concept in my opinion. It's a concept that we're going to be focusing on in this video at least, because that concept about strength is more complicated than it looks, and it will be discussed in a future video, hopefully. So in this one, we have acetic acid, our acid, NH3 ammonia, our base, forming, well, since it's the acid, it will transfer an H+, and what we end up with is CH3COO- and NH4+. Now it's up to you whether you want to put aqueous, but for the sake of time, I will not do that. So if this is the acid, that's a conjugate base. If this is a base, then its conjugate will be, well, a conjugate acid. So there you go. So let's take a look at this next problem. Now NH4+ is unfamiliar. I don't know if that's an acid or a base. We know that that's a base, so this must be an acid. Another way to think about this is, what if we switch the positions? What if we called NH4+ a base and OH- an acid? Well, this would donate an H+, and you would get NH52+ plus O2-. Now that doesn't seem right. I've never seen this before. And to tell you the truth, it probably doesn't exist, because an N with 5 H's attached would exceed its octet, and that's not good. So we can see that OH- will not be the acid in this reaction. It'll actually just be the base of this reaction. So let me just undo all that, and let's take a look at the problem once again. So we can transfer an H+ to find the products. So NH4+ upon losing an H+ will be NH3, and it lost a positive charge, so that positive one becomes neutral. And OH minus plus H plus is always water. And since this was the acid, this would be the conjugate base. This is a base, that's a conjugated acid. So way to go. Now what about this one? Now this one's going to be pretty interesting. I'm just going to show you how it works. So since we're looking at Lewis structures, I am hinting at the fact that we will be looking at the Lewis model of acids and bases, which means that acids accept electron pairs and bases donate electron pairs. So in this case, NH3, we know it to be a base, a weak one in fact, and it's going to donate an electron pair, and it'll actually donate it to that boron. And what you end up with is you get N, H, H, H connected by B, F, F, and F. Now, you might be wondering how this exactly works, because in the past acid-base reactions, we noticed that when we transferred it, that the bond has to be broken right after it is formed. But why did it not happen this time? Well, in this case, boron actually can be happy with 4 bonds, because remember, boron only has 3 valence electrons. So being able to have that extra bond over there, along with those other 3 bonds that it forms, will actually give it an octet. And that makes it happy. So this bond actually works for this boron, and boron doesn't need to break any bonds to, be happy. It's happy where it's at right now. So because it's happy where it's at right now, this is actually the final structure that we get, where this is the base and this is the acid. And we actually don't have a conjugate acid or conjugate base here, because when they react, they actually just combine together, and that's all we have. And I should put the lone pairs on our fluorines, because they have 8 valence electrons, so let me just add those over there. Now let's calculate the formal charges to see the charge on this molecule. Let's see nitrogen. Well, nitrogen has naturally 5 electrons minus 4 bonds is equal to plus 1 formal charge. Boron has 3 electrons naturally minus 4 bonds, and that leads to, well, a negative 1 formal charge. So notice how a plus 1 formal charge and a minus 1 formal charge adds up to, 0. So this molecule overall, NH3BF3, is actually neutral. So we did a great job there. And now let's move on to the very next topic. It's going to get a little bit more complicated here. Well, actually, let's save this for a future video. So that's all for this video. I hope you all enjoyed watching, and have a wonderful day, everybody.